This is the algorithm that is mentioned in the DDPM paper. But why? The reasoning given for the success of many algorithms in deep learning is that it just works. But diffusion is one of the branches of generative AI where currently there is supremacy of high level math. Through this video, I will go through the steps as detailed as possible to derive the algorithms so that the math becomes less daunting, and then you will be able to make even more beautiful algorithms. Hi, my name is Jaidip. I am a senior AI researcher with 14 years of experience, and in this channel, I talk about AI from basics. The goal of AI is to learn from data, adapt to new and complex situations, and solve problems without the need for human interventions. This generally involves some form of intelligent signal generation that cannot be done with the help of some clean mathematical formula. To achieve this signal generation in complicated environments, generative models are used. Generally, there are two classes of generative models that are quite successful: autoregressive models and diffusion models. Diffusion models are widely used for various purposes such as image generation from scratch using a prompt, in painting and conditional image generation, audio and music generation, video generation, drug discovery, training robots for household chores, and many more. Now, to understand what diffusion is, let's backtrack a little bit and we will consider the image example. An image is generally stored as a combination of red, blue, and green pixels because our eyes have cones for these three colors, and in this way we are able to differentiate between a wide range of colors. So there are three channels for the pixels, and each channel has intensity values from 0 to 255 for the corresponding colors. So the dimensions of the image are 1 cross channel cross height into width. Now consider a random combination of these pixel values. It will probably be just some random noise image and not have anything discernible in the image. So you can imagine that a good image would just be a very small subset of the overall class of images that can be denoted by this hyperspace denoted by 1 cross c channel cross height into width. If we can somehow find the boundaries of this subspace, then maybe we will be able to generate an image out of this. GANs work on this idea where the discriminator differentiates between the real and fake images and then conditions the generator model to generate or sample from the subspace where the real reside. Another popular idea has been using variational autoencoders, where the model learns a structured and continuous latent space, and this is used to generate new data. Interestingly, there have been major issues with these two approaches, such as mode collapse in case of GANs and noisy images in case of VAEs. Machine learning has had a history of taking inspiration from nature, and this time we can take inspiration from the diffusion process. You might have observed that when you dissolve one liquid, like let's say some form of a dye, it tends to distribute over the liquid. Thus, diffusion is the net movement of a body of molecules from a place of higher concentration to lower concentration within the domain of fluids. Although called diffusion, what we are more interested is in Brownian motion, which is diffusion of a single particle. The reason for this will be clear later in the video. There is a poem from 60 BC which talks about the random movement of dust. The discovery of Brownian motion is attributed to botanist Robert Brown, who observed the jittery behavior of pollens when working on an experiment. He first thought that pollens had life of their own, but then experimented with inorganic matter as well, confirming that this is not the reason. Albert Einstein proved the relation between the probability distribution of Brownian motion and the diffusion equation. The first complete and rigorous mathematical analysis of Brownian motion was given by Norbert Wiener, and hence the Brownian motion is also called the Wiener process. When we are building a generative model, like a diffusion model for creating images, our ultimate goal is to find the distribution of real images. Think about it. If we knew this distribution, we could simply sample from it and generate perfect images every time. But here is the catch. Finding the true distribution is incredibly difficult. The space of all possible images is enormous, and the underlying probability distribution is complex beyond measure. But wait, do we really need to find the exact distribution? What if we only care about being able to sample from it? This is a crucial distinction. If we can find a method that lets us sample from the true distribution without having to compute it explicitly, we can circumvent the entire problem. And that's exactly what Markov chain Monte Carlo, or as we call it, MCMC, does. Markov chain Monte Carlo is a class of algorithms that does something remarkable. Given a target probability distribution that we don't know, MCMC allows us to construct a Markov chain that we can use to approximate this target distribution. The beauty of MCMC is in its simplicity. The more steps we take in our chain, the closer our samples get to the true distribution. It's like taking a random walk that gradually explores the landscape of probable images. Now, what makes a process Markovian? The key property is this: the current decision only depends on where you are right now and not on how you got there. Your past doesn't matter, only your present state. Think of it like this: if you're standing at a crossroad, a Markovian process would decide what direction to go based solely on where you are standing, not on which roads you took to get there. There is no memory of the journey, only awareness of the moment. In MCMC, we build a chain like structure, literally called a Markov chain. Each state in the chain represents a possible configuration or sample. Between these states, we have transition probabilities that tell us how likely we are to move from one state to another. These transitions are captured in what's called a transition probability matrix. Each entry in this matrix tells us, if I am in state A, what's the probability I'll transition to state B? Let's look at this transition matrix more closely. Each row represents a starting state and each column represents a destination state. The entry at position ij tells us the probability of moving from state I to state j. That's an important property here. Each row must sum to 1. Why? Because if you are in a particular state, you have to go somewhere, even if that somewhere is staying in the same state. The probabilities of all possible transition must account for all possibilities. Now here's where the magic happens. When we start our Markov chain, our initial samples might be far from the true distribution, but as we take more and more steps, as we follow the chain through many transitions, something beautiful occurs. Our samples begin to converge towards the target distribution. In the beginning, it is okay for our approximation to be rough, barely resembling what we are trying to model, but step by step, transition by transition, we get closer. By the time we have taken enough steps, our samples are practically indistinguishable from samples drawn from the true distribution itself. This idea should feel familiar if you have watched our previous video on quantization. Remember the penalty method? We used an iterative process that gradually improved our solution. MCMC follows a similar philosophy. Instead of solving the hard problem directly, we build a process that incrementally approaches the solution. In diffusion, we'll see this exact principle at work. We don't try to directly model the complex distribution of real images. Instead, we build a Markov chain that gradually transforms noise into realistic images, one step at a time. The profound insight here is the power of indirection. We can't easily compute the distribution we want, but we can build a process that samples from it. We can't directly generate perfect images, but we can generate a chain of transformation that gets us there. This is the essence of MCMC and is fundamental to understanding how diffusion models work. We are not finding the distribution, we are building a pathway to sample from it. Langevin dynamics is one of the most popular MCMC methods out there, and it is one of the inspirations behind the theory of diffusion models. Let's start with the math. If we have a probability distribution of P of x that is Markovian, then it will belong to the exponential class of distributions. This is given in equation 1 where P of x is proportional to e to the power negative f of x. Here f of x is some function such that this equation holds. Taking the log of both sides, we get log of p of x equals negative of f of x plus a constant. Now let's assume that we don't have a way to directly sample from this distribution. Instead, we assume we can only know the gradient of the function at every point, that is, del of f of x. If that's the case, we can apply gradient descent to find the modes of the distribution. This is given by equation 2, where x at time t equals x at time t minus 1 minus eta t times the gradient of f of x at t minus 1. Here eta is the learning rate at time step t. If we can find the modes of the distribution, then we can find the areas with peaks in the density. Since in our training data there will be lots of good images. This means going to peaks will result in these good images. Langevin sampling is an interesting modification of this gradient descent algorithm given by equation 3. Here x at time t plus 1 equals x at time t minus epsilon over 2 times the gradient of f at x t plus the square root of epsilon times a Gaussian noise term. Notice we are adding a noise term to each step in the gradient descent formula. Let me show you the difference visually. Here we have a probability distribution with two modes or peaks. These yellow dots show the modes of the distribution, the points of maximum probability density. Now watch what happens when we use standard gradient descent. Starting from this red point on the left, gradient descent climbs up the distribution and it converges to the nearest point. That's it. It gets stuck at this local minima and doesn't explore anything else. Now let's see Langevin dynamics in action. I will start multiple particles from the same region. The particles are being pulled towards the modes of the gradient term, but the noise term causes them to jitter around and explode. Thus, Langevin dynamics explores the entire distribution, not just a single mode. This is exactly what we want for generating diverse samples. But there is a problem with this approach. If we want to speed up the process, we might choose the value of epsilon to be too high, but this can make equation 3 unstable and cause the algorithm to diverge out. So it would be good if we could provide some form of guarantee that the update rule will converge. For this, we will take the help of various algorithms such as the Metropolis-Hastings algorithm. I am not going into those details as that's not the focus of this video. Taking inspiration from Markov chains, let's start by sampling an initial data point x0 from a real data distribution q of x. Think of this as picking a clean image from our dataset. Now, here is where things get interesting. We are going to gradually add noise to this initial data, similar to the physical diffusion process we discussed earlier. We start with our clean image x0 on the right. As we move through time, we progressively add noise at each step. At time t minus 1, the image is slightly noisy. At time t, it's even noisier. And finally, at time capital T, the final time step, we end up with pure Gaussian noise. Notice the arrows between states. The forward process represented by q of xt t given x of t minus 1 shows how we transition from one noisy state to the next. The backward process, shown with the yellow arrow with p theta, is what the backward process will learn, but we'll get to that later. For now, let's focus on understanding the forward direction. Since this is a Markov process, each state only depends on the immediately previous state. It has no memory of earlier states. This memoryless property is crucial for making the math tractable. This diagram and notation may seem confusing, but this is how it's shown in the DDPM paper. It's the reverse process that we need a model for. That is why that is shown from left to right. The forward process is shown from right to left because that can be done using an algorithm, which we will discuss soon. Remember the notation. Q is for forward and P is for backward. X0 means that it's a good image and X capital T is for the noisy image. Because we are dealing with the Markov process, we can express the joint probability distribution in a simple way. The probability of the entire sequence x1 through x capital T can be written as a product of individual transition probabilities. Each transition from xt minus 1 to xt contributes one term to this product. Now let's dig deeper into what happens at each transition step. Remember that a normal distribution is defined by two parameters, a mean nu and a variance sigma square. These control the center and the spread of the distribution. The transition kernel q of xt given xt minus 1 is defined as a Gaussian distribution. Specifically, it's a normal distribution with mean root over 1 minus beta t times x of t minus 1 and variance beta t times the identity matrix I. The mean term root over 1 minus beta t times xt minus 1 contracts or scales down the previous state. This is important because it ensures we are not just adding noise but actually moving towards a standard Gaussian distribution. The variance term beta t into I determines how much noise we add at each step. The identity matrix I means we add the same amount of noise in all dimensions. The beta parameter is crucial. It is our noise variance schedule. It controls how quickly we add noise throughout the diffusion process. Beta values must satisfy a specific ordering. 0 less than beta 1 less than beta 2 and so on, beta t less than 1. They start small and gradually increase, meaning we add noise slowly at first, then more aggressively as time progresses. Now how exactly should beta change over time? This is where variance schedule come in. We can visualize different strategies by looking at signal to noise ratio over time plotted on a log scale. The original DDPM paper used a linear schedule where beta increases linearly from 10 to the power minus 4 to 0.02. This is shown in red and it provides a steady predictable noise addition. But researchers have explored other options. The Fibonacci sequence shown in gold adds noise more gradually at first. The sigmoid schedule in teal creates an S-curve pattern and the exponential schedule in blue decreases the signal to noise ratio rapidly. However, later research discovered that the cosine schedule, shown in green, actually performs better than the linear schedule. The cosine schedule maintains signal information longer and has a smoother transition to pure noise, which helps the model learn better. Notice how the cosine curve stays higher for longer, then drops off more sharply near the end. This characteristic makes it the preferred choice in modern diffusion models. Now here is a challenge. If we want to sample X at time step 500 or higher, do we need to repeatedly apply Q 500 times? You might think of using dynamic programming, but what if we don't want sequential training? There's actually a better method. the reparameterization trick. The reparameterization trick is fundamental to working with normal distributions. If Z follows a normal distribution with mean mu and variance sigma squared, we can write this in a different form. Watch as we transform this distribution. We can shift and scale any normal distribution to a standard normal with mean 0 and variance 1. This gives us Z equals mu plus sigma times epsilon, where epsilon is drawn from a standard normal distribution with mean 0 and variance 1. This simple transformation is the key to everything that follows. Let's apply this to our diffusion process. Starting from the definition of the forward diffusion, as we just saw, we can write xt in its reparameterized form. Now let's introduce alpha t, which equals 1 minus beta t. This substitution will make our equations cleaner. So we can now replace the beta terms. First 1 minus beta t becomes alpha t, then beta t becomes 1 minus alpha t. So we arrive at the current equation, xt equals root over alpha t times xt minus 1 plus root over 1 minus alpha t times epsilon t minus 1. Now comes the magic. We can apply the same trick recursively. Look at xt minus 1 in an equation. It's also a random variable that follows the same pattern. We can substitute xt minus 1 with its own expression involving xt minus 2. Now we distribute the root alpha t term. We get 3 terms, one with xt minus 2 and 2 epsilon terms from different time steps. So here's the key question. Can we combine these 2 epsilon terms into a single term? Yes, we can. Let's see how. The 2 epsilon terms correspond to 2 independent normal distributions, x with variance alpha t times 1 minus alpha t minus 1 and y with variance 1 minus alpha t. From probability theory, when we add 2 independent normal distributions, the result is also normal with the sum of the variances. Let's calculate this sum. Alpha t minus 1 minus alpha t minus 1 plus 1 minus alpha t. Expanding this out, we get alpha t minus alpha t times alpha t minus 1 plus 1 minus alpha t. The alpha t terms cancel, leaving us with simply 1 minus alpha t times 1 minus t times alpha t minus 1. So we can combine our 2 epsilon terms into a single term, root over 1 minus alpha t times alpha t minus 1. So we can see, now can we see the pattern? Our equation simplifies. Xt minus 1 equals root alpha t times alpha t minus 1 times alpha t minus 2 plus root 1 minus alpha t times alpha t minus 1 times alpha epsilon t minus 2. We can keep applying this recursively all the way back to x0. The product of alphas keep expanding until we reach alpha 1. Let's define bar of alpha t as the product of all alphas from 1 to capital T. This is our cumulative product. With this notation, we arrive at our beautiful closed form xt equals root over bar of alpha t times x naught plus root over 1 minus bar of alpha t times epsilon naught. Or equivalently, xt follows a normal distribution with root bar of alpha t times x naught and variance 1 minus bar of alpha t times the identity matrix. This is huge. We no longer need to sample from Q repeatedly. We can directly sample xt at any time step using just x naught and a single noise sample. This makes the entire process much faster. So we see that the reparameterization trick lets us derive a closed form for sampling at any time step. We can jump directly to any point in the diffusion process without sequential computation. This is possible because of Gaussian properties and recursive substitution, and it's what makes diffusion models practical to train. Let's quickly recap forward diffusion. We start with a clean image x0 and progressively add noise through steps x1, x2 all the way till xt. Each step depends on the noise level beta t and the previous image xt minus 1. After t steps, we end up with pure Gaussian noise. Simple enough. But here's the real question. Can we reverse this? Can we start with random noise and turn it into a real image? To do this, we would need to compute p of xt minus 1 given xt, the probability of the previous step given the current noisy image. But computing this probability is intractable. We would need to consider every possible image in existence to calculate this conditional distribution. That's completely infeasible. We can throw neural networks at this problem, but not just any neural network. We can formulate the neural network in an intelligent manner. We train a network with parameters theta to learn p theta of xt minus 1 given xt. The network takes in the noisy image xt and the time step t and outputs a Gaussian distribution with mean mu theta and covariance sigma theta. Theta represents all the neural network weights we'll learn during training. Instead of knowing the exact reverse process, we teach the network to predict it. Second interesting insight is that learning to reverse each intermediate step of the reverse diffusion process may be easier than learning to sample from the target distribution in one step. Taking inspiration from Wiener processes and Brian Anderson, it can be shown that this reverse conditional distribution p of xt minus 1 given xt follows a normal distribution in the forward process is Gaussian given the noise that is introduced is small. Basically, with sufficiently small step sizes, the authors in the DDPM paper said that the discrete diffusion process approaches the solution to a stochastic differential equation, aka Wiener process or the Brownian motion. Now, how do we model the entire reverse trajectory? We use the chain rule of probability. The joint probability of all time steps x1 through x capital T equals the starting noise distribution of p of x capital T multiplied by the product of all the conditional probabilities at each step. So we start with noise, then denoise step by step, where each step is a Gaussian transition. By breaking into small steps, each individual step becomes manageable to learn. Finally, with pure Gaussian noise, p theta of xt is a standard normal distribution, mean of 0, unit variance in all dimensions. This is what we achieve after t forward steps, and it's our starting point for reverse diffusion. We sample random noise from this distribution and then use our learned neural network to progressively denoise it step by step until we generate a real image. Thus we get from pure noise to realistic images. Now before going forward, we need to understand about evidence lower bound or ELBO, which are used in variational autoencoders as well. In diffusion models, we work with observed data x and latent variables z. Our goal is to learn the probability distribution p of x. But here's the problem. We have two ways to compute p of x and both are intractable. On the left, we can integrate over all latent variables, but this problem is generally computationally impossible to evaluate. On the right, we can use Bayes' rule, but this requires the true posterior pz given x, which we don't have access to. So how do we solve this? As a solution, we can try to approximate the true posterior instead of using pz given x, which we can't compute. We learn an approximate posterior q phi of z given x, where phi represents learnable parameters. Notice that this p and q are different than the p and q notation that we have discussed before related to forward and backward diffusion. Here p means the real probability distribution and q means the approximate distribution that we are coming up with that we will use instead of p. This approximate distribution follows the same factorization property. The joint distribution q of z and x equals the conditional q of z given x times the marginal q of x. Now let's derive an important relationship. The marginal distribution q of x can be written as the integral of the joint distribution. If we substitute our factorization from before, we get q of x equals the integral of q of z given x times q of x dz. Since q of x doesn't depend on z, we can factor it out of the integral. This gives us q of x equals q of x times the integral of q of z given x dz. We remove q phi x from both sides. We get 1 is integral of q of z given x. Thus we can see that any integral of q of z given x over all z must equal 1. This makes sense because probability distributions must integrate to 1. We can multiply both sides by log p of x without changing the equality. This gives us log px equals log px times the integral. Since log p of x is constant with respect to z, we can move it inside the integral. And finally, we can write the integral as an expectation over our approximate posterior. This gives us log p of x equals the expectation of log p of x. Recall from earlier that p of x can be written as the ratio of the joint distribution pxz over the conditional pz given x. So we are going to introduce our approximation of q of z given x into this expression. We get log p of x equals the expectation of the log pxz over pz given x. Now we'll multiply the numerator and denominator by q of z given x over q of z given x, which equals 1. So it doesn't change the value. After multiplying by q over q, we can use the logarithm property that log of a times b equals log of a plus log of b. This splits our expression into two terms, the log of pxz over qz given x plus the log of qz given x over pz given x. Now we use the linearity of expectation. The expectation of x plus y equals the expectation of x plus the expectation of y. So we can separate this into two distinct expectation terms. So here it is. Look at what we have derived. The first term is what we call the ELBO, the evidence lower bound. The second term is the KL divergence between our approximate posterior q and the true posterior p. Critically, KL divergence is always greater than or equal to 0. Since the KL term is non-negative, we can remove it to give an inequality. Log p of x is greater than or equals to the ELBO. This is the evidence lower bound. It provides a lower bound on the log probability of our data. Why is it called a lower bound? Think of it like a lever. It's difficult to leave the original object directly than by computing log of px, which is intractable. But with the lever, we can apply force at a different point. The ELBO on the left is computable, and by maximizing it, we indirectly push up the intractable log px on the right. So here's a training strategy. Instead of trying to maximizing log of px directly, which is intractable, we maximize the ELBO. This indirectly maximizes log of px and is equivalent to maximizing the KL divergence between our approximation and the true posterior. In the previous section, we derived the ELBO equation for DDPM diffusion. Now we'll decompose it into three interpretable components so that the loss function is tractable. In the previous section, we had come up with the equation for the ELBO. Along similar lines, we can say that the evidence lower bound, an expectation over the log ratio of our model's joint probability to the forward and backward diffusion process. This looks like the log of the expectation of p by q over all the time steps. Based on our understanding from the previous section. Similarly, here we start with the log evidence, the log probability of our data. We introduce our forward process q as an important sampling distribution, multiplying and dividing by it. This clever trick doesn't change the value. Now we have the expectation of a ratio under q. Jensen's equality tells us that the log of an expectation is greater than or equals to the expectation of the log. Our ELBO is now the expected log ratio between the true and approximate distributions. We expand the reverse process as the product of the prior and all backward transitions. Since our forward process is Markovian, we can condition on x0 without changing probabilities. This separates the first denoising step from the rest. Here's the key trick. We apply Bayes' rule to rewrite the forward conditional in terms of the backward conditional and marginals. So we separate ELBO into two parts, E1 and E2. E1 contains the H terms, the starting x0, x1 and the final xt. E2 contains all the middle denoising steps from t equals 2 to capital T. We break them apart because in the next few steps we'll focus only on E2. This keeps our equations manageable. We are not doing anything with E1 yet, so there is no need to worry about those terms through every step. This is just so that I can show it clearly in this video. So we separate out the terms in the product. Let's have drum roll please. We write out the product explicitly as individual fractions. Notice q of x2 given x0 appears in both the denominator of the first fraction and the numerator of the second, so they cancel. The same thing happens with q of x3 given x0, denominator of the second and numerator of the third. Bam! Another cancellation. This pattern continues for all middle terms, q of q4 given q0, q of q5 given q0, all the way till q of qt minus 1 given q0. Like dominoes falling, each middle term cancels with its neighbor. Only the boundary term survives, q of q1 given q0 over q of qt given q0. We can replace this in the E2 term. Now we bring E1 and E2 back together. In this equation, we have three separate log terms inside the expectation. The first containing p of xt into p theta x0 given x1 over q of x1 given x0. And the second contains q of x1 given x0 over p of x capital T given x0. And the third being the product term from E2. Notice that the function q of x1 given x0 in the denominator of the first term cancels with the q of x1 given x0 in the numerator of the second term. After cancellation, only q of x final t given x0 remains in the denominator. Also the last term, since we are dealing with sums of logarithms, the underlying structure represents product of ratios. We convert the product back to a summation for easier computation. Thus, using linearity of expectations, we can split this into three separate losses, L0, L final t and a sum of intermediate terms. Each has a specific role. L0 is the reconstruction term. It matches how well we recover the clean image from the first noisy step. This is optimized using Monte Carlo sampling. LT measures how close our final noise matches a standard Gaussian prior. Crucially, this has no trainable parameters. It is just a constant. The sum of L terms is where learning happens. Each term compares our model's denoiser to the perfect posterior at that timestamp. This decomposition is brilliant for three reasons. Each expectation now depends on fewer variables, giving lower variance estimates. Each term has a clear interpretation, and we can compute them efficiently during training. Thus, we have transformed a complex intractable objective into three manageable components: reconstruction, prior matching, and denoising quality. This elegant formulation is what makes DDPM training practical. Sampling algorithm. We have derived the ELBO loss, but optimizing KL divergences between arbitrary posteriors is difficult. In this section, we'll use Gaussian assumptions to make the problem tractable. Using Bayes' rule, we can flip the conditioning in our posterior distribution. This allows us to express q of xt minus 1 given xt x0 in terms of quantities we can compute. From the forward diffusion process and Markov property we discussed before, remember that q of xt given x0 equals to the normal distribution of xt with mean root of alpha t x naught and variance 1 minus alpha t into identity. We can write our posterior as a product of three Gaussian distributions. This form is based on the mean and variances that we had defined before. Recall the probability density function for a Gaussian distribution. F of x is 1 by root over 2 pi sigma square into e to the power minus of x minus mu whole square divided by 2 sigma square. We can use this form in our derivation. So now for q of xt minus 1 given xt x naught, using this definition we can expand the Gaussians in the form of the exponentials. These multiplication and division of Gaussians become addition in the exponent land. Moving forward, we know from our high school level math a minus b whole square is a square minus 2ab plus b square. So we can expand each square term in our expression. We group all terms involving only xt and x naught into a constant function c of xt x naught. Since we are conditioning on these values, we can treat them as constants. A constant in the exponent means that the distribution is proportional to the exponent. We can remove c of xt x naught from our expression using e to the power x plus c is c of e to the power x, which is proportional to e to the power x. We factor out the common denominators and reorganize the terms. The goal is to get everything over a common denominator, 1 by alpha t into 1 minus alpha t minus 1 bar. In the numerator, alpha t minus alpha t into alpha t minus 1 bar plus 1 minus alpha t simplifies beautifully. The alpha t terms cancel, leaving us with 1 minus alpha t bar. Next, we are factoring out the terms related to x square t minus 1. For this, we can make the necessary changes in the fraction involving xt minus 1. In the next step, we can change the constant fraction at the start to the form 1 by 2 sigma square. Recognize this is a Gaussian distribution in standard form. We can now extract the mean mu of q and variance sigma q. The variance is clean, but the mean still contains both xt and x naught. Previously, when defining forward diffusion, we had come up with the formulation that xt equals to root of over alpha t bar into x naught plus root over 1 minus alpha t bar into epsilon naught. Flipping this means that x naught becomes a ratio of xt minus root over 1 minus alpha t bar into epsilon naught divided by root over alpha t bar. We substitute this expression for x naught into our mean formula. In the denominator of the substituted x naught, the root over alpha t bar we can expand to root over alpha t into root over alpha t minus 1 bar. So root over alpha t minus 1 bar and root over alpha t minus 1 cancels, leaving us with 1 minus alpha t into xt minus root over 1 minus alpha t bar into epsilon naught. Now we expand the brackets and separate the terms. Notice the alpha t xt terms appear with opposite signs, so they cancel. We can now separate into two parts, coefficients of xt on the left and coefficients of epsilon naught on the right. Look at the xt coefficient. 1 minus alpha t bar appears in both numerator and denominator, so it cancels. Similarly, in the epsilon naught coefficient, root over 1 minus alpha t bar cancels between numerator and denominator. After cancellation, we have a much cleaner fraction. Now we factor out 1 over root of alpha t to get the final beautiful form. The mean is the scale factor times current noisy image xt minus the predicted noise weighted by 1 minus alpha t over root 1 minus alpha t bar. This is the perfect denoising mean our model needs to learn. Our neural network will model this by predicting epsilon theta Now we can write the practical sampling algorithm. This is how we actually generate images from pure noise. We start with pure Gaussian noise xt, sampled from normal distribution with mean 0 and unit variance. This is completely random, no structure, no image, just noise. We loop backwards from t to 1. At each time step, we predict and remove a bit of noise. We sample fresh Gaussian noise z at each step except the final step. This maintains stochasticity in our generation process. This is the heart of DDPM. We scale xt by 1 over root of alpha t, subtract the predicted noise, epsilon theta xt t weighted by 1 minus alpha t divided by root over 1 minus alpha t bar, and add random noise sigma tz for stochasticity. Our neural network epsilon theta predicts what noise was added at this time step. After t iterations of gradual denoising, we have recovered a clean image x naught. This iterative refinement is what makes diffusion models so powerful. We have journeyed from intractable KL divergences to a practical algorithm. The Gaussian assumptions give us closed form expressions for the mean and variance, and the reparameterization lets our model predict noise instead of images directly. Finally, we have all the ingredients in place for defining the training algorithm and deriving the final loss. In our case, we have two Gaussians with the same dimension, the ground truth posterior, q of xt minus 1 given xt x naught, and our model p theta xt minus 1 given xt. The key insight, both share the same variance, sigma qt. So variance in both cases is sigma square qt into identity. The neural network only learns the mean nu of theta. This dramatically simplifies the optimization problem. To train our diffusion model, we need to minimize the KL divergence between the ground truth posterior and our learned model. Funny thing about KL divergence is similar to situations where maybe you feel close to them, but they don't feel as close to you. For multivariate Gaussians, the KL divergence has a specific form. The KL divergence between two Gaussians has four terms, which is log ratio of covariances, dimension d, trace of covariance products, and a mean difference quadratic form. From the denoising loss term, our denoising loss wants to minimize this KL divergence. We can rewrite it as an argmin over our model parameters theta. So now we expand our KL divergence and write it in similar manner with the four terms. Now the first term, the log ratio of identical covariances is log of 1 equals to 0. The trace terms give d, which cancels with minus d. We are left with just the mean difference terms. Substituting the specific variance form, we get a scaled L2 norm between the two means. Now we have the derived expressions for nu q and nu theta. Nu q comes from the ground truth denoising step. Nu theta is what our network learns to predict. So now we substitute the expressions for nu q and nu theta. When we expand both inside the norm, something very interesting happens. The xt by root alpha t terms appear in both means with opposite signs. They completely cancel out, leaving only the noise terms. So we can factor out the coefficient that multiplies both epsilon terms. When we take it outside, the coefficient gets squared. Note that beta t is 1 minus alpha t, so we can replace that in the numerator. So here's the final loss function. The neural network epsilon theta predicts the source node epsilon naught. We minimize the L2 distance between true and predicted noise. Since xt is root over alpha t x naught plus 1 minus alpha t bar root over 1 minus alpha t bar epsilon naught, we can say that the final loss function, or we can put that and expand that as the form for x naught. And this leads to the to algorithm 1 for the training procedure. This screenshot is taken from the paper. As you can see, we repeat the form where till convergence, and sample x naught, sample at time step t, and sample noise epsilon. Then take a gradient step on the noise prediction error as we have derived, and continue until convergence. The elegance of this approach: we are not predicting images directly, we are predicting the noise that was added. This is much easier for the neural network to learn. The training loop becomes simple: add noise to images, train network to predict it back. That's it, everyone. Honestly, if you have made it this far, give yourself a pat in the back. There is quite some high level math here. We started with defining what is diffusion, how maybe we can apply diffusion to generate images, and then formulated algorithms for the training and sampling algorithms. Do let me know if you find the video to be helpful. What other videos do you want me to cover on my next video? Thanks for watching. Have a great day.